Hi everybody. So in this video we will continue with chapter 3, sequences and series, specifically 3.5, the binomial theorem. So first of all, we have to say that a binomial is a polynomial with two terms. So x plus y is an example of a binomial. In principle, it's easy to raise x plus y to any power, but raising it to high powers would be tedious. So what we're going to do here is find a formula that gives the expansion of x plus y to the power of n for any positive integer n. And this is what's called the binomial theorem. Now let's look at some particular cases of the expansion of x plus y to the n. So notice that if we do x plus y to the 0, that just equals 1. If we do x plus y to the 1, that equals x plus y. If we do x plus y squared, that equals x squared plus 2xy plus y squared. If we do x plus y cubed, then that's going to be x cubed plus 3x squared y plus 3xy squared plus y cubed, and so forth with all these expansions. So there's several things to notice here after looking at these expansions. First of all, notice that there are n plus 1 terms. So n is the exponent. Notice that when it's to the power of 0, there's one term. When it's to the power of 1, there's two terms. When it's to the power of 2, there's three terms, and so forth. Now let's take a particular case. Let's say this last one, x plus y to the 6. Notice that there's a pattern for x here. X starts to the power of n, right? In this case, n is 6. So it starts with 6 and gradually goes down. So notice that then you have x to the 5, x to the 4, to the 3, to the 2, to the 1, and then 0. For y, it's the opposite. It starts with y to the 0, then y to the 1, y to the 2, y to the 3, y to the 4, y to the 5, and y to the 6. The other aspect to consider here is the coefficients of the terms. Notice that they are symmetric and they follow a pattern. So for x plus y to the 0, it starts with 1. With x plus y to the 1, the coefficients are 1 and 1. For x plus y squared, they are 1, 2, and 1. Now notice that there's a pattern here. Notice that for the third example, or where x plus y is cubic, we would get 1, 3, 3, and 1. But notice that that's the same as adding 1 plus 2 and 2 plus 1 and just keeping the outside coefficients as 1. 1, 4, 6, 4, 1. And notice that you see that pattern here. 1, 4, 6, 4, 1. How about if it's to the power of 5? Well, it would be 1, 5, 10, 10, 5, 1. Remember that I'm just adding this with this. So 1 plus 4, 4 plus 6, 6 plus 4, 4 plus 1. And then I keep the ones on the outside. And then the last one, notice that it would be 1, 6, 15, 20, 15, 6, and 1. And you can see that here, 1, 6, 15, 20, 15, 6, and 1. Well, what we see here, this is what's called Pascal's triangle. And the interesting thing is that you can recursively find the coefficients of the next expansion by adding the terms of the previous expansion, just like we did. But there's a problem. What happens if we have, say, x plus y to the 20? Well, this process of using Pascal's triangle would be too lengthy, too tedious. So that is where the binomial theorem, which by the way is given in chapter 5, the proof, we will see that when we get to chapter 5. What I'm saying is that it would be too complicated to do it with Pascal's triangle. So we are going to take a look at the binomial theorem. So here we are on example 3.22, and it says, use Pascal's triangle to expand 2k minus 3 to the power of 5. So notice that to the left, I already have Pascal's triangle, and this here would be the coefficients when n is to the power of 5. So let's just write this over here. This would be 2k minus 3 to the 5. So what we do is that we write the first coefficient, which is 1, and remember that we start with the first term, which is 2k, right, the term to the left. So 2k is going to be to the power of 5. Negative 3 is going to be to the power of 0. So we don't write that. Then we go plus the next coefficient. So the first one was 1, the next one was 5. So 5, and then it's going to be 2k to the power of 4. And then negative 3 will be to the power of 1. Okay, so the next one, plus 10, the next coefficient, and then 2k will now be to the power of 3, and negative 3 will be squared. Next one, 10 again as a coefficient, as we can see here, and we're going to get 2k now to the power of 2, and negative 3 to the power of 3. This plus the next coefficient, 5 times 2k to the power of 1, and then negative 3 to the power of 4. And finally, it's going to be the last coefficient, which is 1, as we see here, and 1 times, well, 2k will be to the power of 0, so we don't write it, but we'll get minus 3 to the power of 5. So all we have to do now is expand this, and we're going to get 32k to the 5 minus 240 times k to the 4 plus 720 k to the 3, and then we have a minus 1080 k squared plus 810k, and then finally minus 3 to the 5, that's going to be negative 243. So this would be the expansion of 2k minus 3 to the 5 using Pascal's triangle. So like I said before, this method is inefficient if we want to do an expansion of, say, x plus y to the 20, because then we would have to continue doing Pascal's triangle, and this would just take too much time, right? So let's take a look at something called the binomial coefficient. So here we have the definition for the binomial coefficient, and it says, with n and r as non-negative integers such that n is greater than or equal to r, the binomial coefficient, and this is a notation, notice that you have two different kinds of notation that are the same, and this is something from probability. This is what's called a combination. So n combined with r, which is also parenthesis n over r, is equal to n factorial over r factorial times n minus r factorial. So, for example, 3.23 part A, they say find the value of 7 combined with 3. So this is just the application of the above formula. So this would be the same as 7 factorial over 3 factorial times 7 minus 3 factorial. Okay, so remember that factorial, if you have something like 7 factorial, that means 7 times 6 times 5 times 4 times 3 times 2 times 1, and that is for any number that has a factorial. So let's rewrite this as 7 factorial over 3 factorial times 4 factorial. So if we don't have a calculator, we can simplify this by going 7 times 6 times 5 times 4 factorial. And then we have 3 factorial times 4 factorial. So notice that we can cancel out 4 factorial we still have 7 times 6 times 5. And then 3 factorial is 3 times 2 times 1. So notice that we would cancel the 6 out with this too, right? So that means that finally we're going to get the answer, which is 35. So let's take a look at B. So for B, they want us to find the binomial coefficient with this, right? 7 combination 4. So this is going to be 7 factorial over 4 factorial times 7 minus 4 factorial. So 7 factorial over 4 factorial times 3 factorial. So very similar to what we did before, we could say this is 7 times 6 times 5 times 4 factorial. So this over 4 factorial times 3 factorial. We could have this canceled out with this. And as we saw before, 3 factorial is 6. So we're left with 35 again. So notice that that means that these two expressions are equivalent. Let's take a look at C. So for C, we have 7 and 0, right? So we have to do the combination with these. So this is going to be 7 factorial over 0 factorial times 7 minus 0 factorial. Now, one thing we have to be clear about is that 0 factorial is equal to 1, not equal to 0. Some people confuse that, but this is equal to 1. So notice that this is the same as 7 factorial over 7 factorial, and this is simply going to be 1. D is also similar because if you look at D, which says do the combination with 7 and 7, this is going to be 7 factorial over 7 factorial times 7 minus 7 factorial. So notice that this will cancel out with this, and this is simply going to be 0 factorial, which is 1. Therefore, this is equal to 1. So notice that these two are also equivalent. And this is something important because you will notice that this helps with the pattern of finding the coefficients for binomial expansion. Next, we have example 3.24, and it says calculate each binomial coefficient. So let's do this manually first. So notice that first we have 6 and 0, and recall that this is equal to 6 factorial over 0 factorial times 6 minus 0 factorial, and then this is just going to give us 1. Then we have 6 and 1, so this is going to be 6 factorial over 1 factorial times 6 minus 1 factorial, and this is going to be 6 factorial over 1, because 1 factorial is 1, and then 6 minus 1 will be 5 factorial. So notice that this would just leave us with 6. Then we have 6 and 2. So this would be equal to 6 factorial over 2 factorial times 6 minus 2 factorial. And this is 6 factorial over 2 factorial times 4 factorial. But then again, this is going to be 6 times 5 times 4 factorial. And this over 2 factorial times 4 factorial. This would cancel out. Now 2 factorial is just 2, because it's 2 times 1. So then this would be gone together with this, right? We would just divide both by 2. So we're going to get here 15. Okay, now let's do 6 and 3. And this is going to be 6 factorial over 3 factorial times 6 minus 3 factorial, or 6 factorial over 3 factorial times 3 factorial. And then this would be 6 times 5 times 4 times 3 factorial over 3 factorial times 3 factorial. This would cancel out. Remember that 3 factorial is 6, right? 3 times 2 times 1. So this and this can cancel out. And we will be left here with 20. And then if we continue the process, let's say with 6 and 4, for that one, you should get, if you do it manually, for that one you should get 15. For 6 and 5, you're going to get, if you do the math, you're going to get 6. And then if you do 6 and 6, you're going to get 1. Now what I want to do next is compare the results that we just got with the Pascal triangle for the case where n is equal to 6, which is this one. Notice that we get the coefficients by using this algorithm. How so? So notice that on top we have the exponent, which is 6, and then below we have the numbers increasing from 0 to 6. So that means that we would have n plus 1 coefficients, which is always the case. So notice that first we got 1, which is this one here. Then we got 6, which is this 6 here. Then we got 15, 15, 20, 20, 15, 15, 6, 6, and 1, and 1. So now we are ready to actually state the binomial theorem. So in the previous example, we were able to see that we could generate the coefficients of an expansion when it was to the power of 6 by using the binomial coefficients, right? We said that we would go with 6, 0, and then 6, 1, and then 6, 2, and then 6, 3, 6, 4, 6, 5, and finally 6, 6. And this would generate the coefficients for the binomial to the power of 6, because this would give us 1, this would give us 6, this would give us 15, 20, 15, 6, and 1. So we could generalize for any power, right? So we could say the pattern is n0, where n, of course, is the power of the binomial, and then n1, and then n2, and so forth, all the way to n, right? That's what we see here. This is precisely the binomial theorem. So if you have a binomial to the power of n, then this is going to be equal to the following. Notice that first we have the first coefficient, and then x to the power of n. The second coefficient, x to the power of n minus 1, and then we have y appearing for the first time, so y to the 1. Of course, before, y here was to the power of 0. Then we have the next coefficient, x to the power of n minus 2, y squared, plus the next coefficient, x to the power of n minus 3, y to the power of 3, and so forth. So we get a pattern. And this would be previous to last, right? So n over n minus 1, x to the 1 times y to the n minus 1, and then finally n over n for the coefficient, and y to the n. This is the same thing, but using the other way of writing a combination, right? It's the same thing. Now here is something interesting because we could compact it using the terminology of a series. So notice that here we can see it. It's a series from I equals 0 to n of, and this would be the coefficient using combinations, right? So n over I times x to the power of n minus I times y to the power of I. And this is a definition we're going to need to use to solve some examples that we will see shortly. So here we are in example 3.26, and it says, use the binomial theorem to expand x plus y to the 7. So remember that this would be then x plus y to the 7 is equal to, and we start with the coefficients, right? So 7, 0, and then x to the 7 plus 7, 1, x to the 6, y to the 1, right? Plus 7, 2, x to the 5, y squared, plus 7, 3, x to the 4, y cubed plus 7 and 4, x to the 3, y to the 4. And then 7, 5, x squared, y to the 5, plus 7 and 6, x, y to the 6. And finally, 7 and 7, and y to the 7. And then if you do all the math here, this is going to equal x to the 7 plus 7x to the 6y plus 21 x to the 5 y squared plus 35 x to the 4 y cubed plus 35 x to the 3 y to the 4 plus 21 x squared y to the 5 plus 7 xy to the 6 plus y to the 7. Okay, so here we are with the emulator, and I'm going to show you how to do a combination, which is what would give us a coefficient for one of these terms when we expand them, when you expand the binomials using the binomial theorem. So go to Math, and then scroll to the right where it says Probability, PRB, and notice that the third function you have is the combination, NCR, right? Number 3. Okay, but this is an older version of the calculator, so I have to do something first. So let's suppose that I'm going to do 7 over 0, right? So I would have to write the 7, and then now I would go to Math and go to Probability, and we hit Enter there at number 3. So 3, notice that it says 7 NCR, and then I said we were going to do 7 over 0. So there, just hit Enter, and notice that it gives us 1. So you can do that for any case. And let's say 7 and 5. So let's say 7, and then we go Math, Probability, and then Combinations, which is number 3. And we said 7 and 5. Let's see what that gives us. It gives us 21. So next we have example 3.27, which is very similar to example 3.26, where they ask us to do an expansion. So this would be 2k minus 3 to the power of 5. So we follow the same procedure, right? This will be 5, 0 for the coefficient, and then 2k to the 5. Next step, 5, 1, and then 2k to the 4, and negative 3. And then 5, 2, 2k to the 3, negative 3 squared, right? And then we have 5, 3, 2k squared, negative 3 to the 3. And then 5, 4, and we have 2k, negative 3 to the 4, and then the final one, right? 5 and 5, and then 2k would be gone, and this is negative 3 to the 5. So you can use your calculator as I showed you just before, and you're going to get here 32k to the 5 minus 240k to the 4 plus 720k to the 3 minus 1080k squared plus 810k minus 243. Next we have example 3.28, and it says find the term containing a to the 3 in the expansion 2a minus 3b to the power of 9. So this is where we would use the definition of the binomial expansion as a series. Remember that in general we said that x plus y to the n is equal to the sum from I equals 0 to n of the combination, right, of n over I times x to the power of n minus I times y to the I. So that was in general. For this particular case, so we would say 2a minus 3b to the 9 is equal to the sum from I equals 0 to 9 of 9 over I times, in this case, x is going to be 2a, right? So 2a to the power of 9 minus I times y, which in this case would be minus 3b to the power of I. So they're asking for the term containing a to the 3. So the only way we can get a to the 3 is here, right? So basically we need 9 minus I to be equal to 3. So that means that I is definitely going to be 6. So it would be the term where I is 6, which is the 7th term. But let's find it. So we would say, okay, 9, 6. Notice that we're just substituting I with 6. So this times 2a to the power of 3, right? Because 9 minus 6 is 3. And this times minus 3b to the power of 6. So we can just plug this into the calculator, and we're going to get a huge number here, 489,888, a to the 3 and b to the 6. Next, we're going to do example 3.29, and it says find the term independent of x in a. So let's do a, and it says 2x squared minus 3 over x to the power of 9. So what does it mean, the term independent of x? A term that is independent of x means that you're going to have a constant that is not multiplying x. In other words, x to the 0. Okay, so how can we get x to the 0? So let's remember that the general rule for this case, we can just write it as, let's write it as 9 over k, and then we would say this times 2x squared to the power of 9 minus k, and this times minus 3 over x to the power of k. Okay, so what do we do next? All right, let's just focus on x because that's what needs to be canceled out. So in other words, we can rewrite this just in terms of x. We would say x squared and this to the power of 9 minus k, and then this times x to the minus 1, right, because it's below. So x to the minus 1 to the power of k. When is this going to equal x to the 0? In other words, for which value of k will x cancel out? So what we would do here is, let's expand this first one. So we would get x to the power of 18 minus 2k times x to the minus k. How can this equal x to the 0? So this becomes a problem of the exponents only. And notice how we get that 18 minus 3k is equal to 0. So the solution here is obviously going to be k equals 6. 9 in combination with 6, and we would get 2x squared to the power of 9 minus 6, so this to the power of 3, times negative 3 over x to the power of 6. So we know that the x's are going to cancel out, and we're going to get 489,888. Okay, so I will leave part B, since it's so similar, as an exercise for you guys. So now we are in example 3.30, which will be the last one on this video. And it says find the coefficient. So they want us to find the coefficient only, right, of b to the 6 in the expansion of 2b squared minus 1 over b to the power of 12. So let's remember that the general term in this case is going to be 12 over I, and then we have 2b squared to the power of 12 minus I, and this times negative 1 over b, and here we have this to the power of I. And then the question is, what's the coefficient when b is to the power of 6? So we have to consider the case for b, and b needs to be to the power of 6. So let's just focus on b, on the variable. So we could rewrite this as b squared to the power of 12 minus I, and let's write this as b to the minus 1 to the power of I. So this has to equal b to the 6. So I would say, okay, 24 minus 2i minus I, when is this going to equal 6? And in this case, we're going to get 24 minus 3i is equal to 6. So minus 3i is going to equal negative 18. So notice that we're going to get that I is 6, just like the last case. So I is 6. Now we can just plug that in here and solve, right? So we would say, okay, so 12, and since they only want the coefficients, we're only going to focus on the coefficients. So 12 and 6, this would give us the coefficient, but we also have to multiply by the constants that we have in this expression. So the next one would be 2, and this 2 would be to the power of 6, right? Because 12 minus I, and we saw that I is 6. And then this times negative 1, and to the power of 6. So this is going to equal 59,136. If they had asked us for the term, then this would be 59,136 b to the 6. But they only want the coefficient, so that would be this.